Hey there, science fans. Today we're diving into the exciting world of digital systems. What are they? Well, they're all around us. From your smartphone to your car, digital systems are the brains behind countless devices. In simple terms, a digital system uses digital signals to process information. These signals are like switches, either on or off, represented by ones and zeros. This binary code forms the basis of all digital technology. Pretty cool, huh? Analog systems deal with continuous signals, while digital systems deal with discrete values. They're more accurate, reliable, and efficient than analog systems. Plus, they allow for complex operations and data storage, making them essential for today's technology. Just like we use languages to communicate, computers use number systems. While we use the decimal system, base 10, with 10 digits, computers primarily use the binary system, base 2, with only 2 digits, 0 and 1. But that's not all. Computers also use other number systems like octal, base 8, and hexadecimal, base 16. These systems provide a compact way to represent binary data, making it easier for us humans to understand. Binary arithmetic, the way computers perform math, is surprisingly simple. It involves basic operations like addition, subtraction, multiplication, and division, using only zeros and ones. To represent negative numbers, computers use techniques like 2's complement. Other important codes include gray code, which minimizes errors in digital systems, and BED, binary coded decimal, which bridges the gap between decimal and binary representations. Imagine tiny electronic switches that control the flow of information. These are called logic gates, and they're the fundamental building blocks of digital circuits. Each gate performs a specific logical operation like AND, OR, or NOT. Boolean algebra, a mathematical system developed by George Boole, helps us understand and design these logic circuits. It uses simple rules to manipulate logical expressions, just like we use algebra for numbers. We can simplify complex logic expressions using Boolean laws, making the circuits more efficient. Carnot maps, visual tools that look like grids, help us further simplify expressions and design optimal circuits. Now that we know about logic gates, let's combine them to create more complex circuits. These are called combinational logic circuits, where the output depends solely on the current input combination. We can design circuits for various functions, like adding 2 binary numbers or selecting specific data lines. Multiplexers and demultiplexers act like data selectors, while encoders and decoders convert between different data representations. Adders and subtractors, as their names suggest, perform arithmetic operations on binary numbers. These circuits are essential for computers to perform calculations. Section 5. Sequential logic. Circuits remembering the past. Unlike combinational circuits, sequential logic circuits have memory. They can store information and use it to influence future outputs. This ability is crucial for tasks like counting and data storage. Memory elements like flip-flops and latches are the key to this memory function. They act like electronic switches that can remember their previous state. We can design counters using flip-flops to keep track of events or create state machines that control complex sequences of operations. Timing diagrams and state diagrams help visualize the behavior of these circuits over time. Section 6. Timing and synchronization, keeping everything in order. In digital systems, timing is everything. Clock signals, like tiny metronomes, ensure that all parts of the circuit operate in sync. Without proper timing, data can get corrupted and circuits may malfunction. Setup and hold times are critical parameters that dictate how long data signals need to be stable before and after the clock edge. Violating these timings can lead to unpredictable behavior. Asynchronous circuits operate independently of a clock signal, while synchronous circuits rely on the clock for synchronization. Each type has its advantages and disadvantages depending on the application. Section 7. Programmable logic devices, hardware that can be reprogrammed. Programmable logic devices, or PLDs, are like chameleons of the digital world. They can be reconfigured to perform different functions. This flexibility makes them incredibly versatile for various applications. CPLDs and FPGAs are 2 popular types of PLDs, offering different levels of complexity and performance. Designers use special software tools to program these devices, creating custom digital circuits. Section 8. Designing digital systems from idea to reality. Designing digital systems is like building with electronic Lego bricks. We start with an idea, translate it into a logical design, and then implement it using hardware description languages, or HDLs, like VHDL and Verilog. HDLs allow us to describe the behavior of digital circuits using text-based code. Simulation tools help us verify the design before implementing it in hardware, ensuring that everything works as intended. Digital system design follows a structured flow from specification to testing and verification. Different methodologies and best practices ensure efficient and reliable designs. Section 9. Digital systems in action, applications in the real world. Digital systems are everywhere. Microcontrollers, tiny computers on a single chip, power countless devices from your microwave to your car's engine control unit. Digital signal processing, or DSP, is another exciting field where digital systems shine. DSP algorithms analyze and manipulate signals like audio and video, enabling applications like noise cancellation, image compression, and medical imaging. Real-world case studies showcase the transformative power of digital systems. From self-driving cars to advanced medical devices, these systems are shaping the future of technology.